Now next is the per unit sequence model or the sequence network of three-phase two-winding transformer. This is the equivalent circuit of a transformer, the primary side, secondary side impedances, and this is the magnetizing component and the working component, that is resistance and reactance represented, and this is the high voltage side and low voltage side. So here what I am considering is the current flowing through the shunt component is very much less, that is this shunt component, the current which is flowing through the shunt component is very much less compared to the current flowing through the winding. So I am going to neglect this shunt component, and also the resistance is very much less than the reactance. So I am going to neglect this resistance and represent the winding with the leakage reactance, which is represented by JXL. And by considering by not considering the shunt component in the resistance, I am going to represent the three-phase two-winding transformer as JXL, the leakage reactance, and this alpha, which is nothing but the phase displacement, alpha equal to plus or minus 30 degrees. So based on this, we are going to develop the positive sequence, negative sequence, and zero sequence networks. Now coming to the positive sequence network, the high voltage side, the voltage is represented by VH1, and on the low voltage side it is VL1. Now the reactance is denoted by JXL, and this particular symbol indicates that there is a phase displacement of 30 degrees in the positive direction, that is the voltage on the high voltage side leads the voltage on the low voltage side by 30 degrees. So this slash this side represents that the high voltage is, sorry, I said earlier as lagging, but it is leading, as I have mentioned here. The high voltage leads the low voltage by 30 degrees. Now coming to the negative sequence network, that is the high voltage and this is the low voltage. Now in the negative sequence network, the high voltage side, that is VH2, lags VL2 by 30 degrees, which is represented like this, and the reactance is given by JXL. Now coming to the zero sequence network, here we have different cases that we have to consider. Now consider star-star transformer with neutral grounded on HV and LV side. That means on both the sides, on HV side and LV side, the transformer is connected in star-star and the neutral is grounded. So these are the phases which I am representing here as A, B, C. The capital letters represent the terms on the high voltage side and the lowercase letters represent the terms on the low voltage side. So considering the star connection on the high voltage side, this H1, H2, H3 are the high voltage windings that are represented. Capital, that is IA, IB and IC are the currents flowing through it. And since we have considered that the neutral is grounded, the neutral impedance is denoted by Zn. Here this N is capital. Similarly on the low voltage side, the same notation, but instead of H I have represented the windings as L1, L2 and L3 and the currents IA, IB, IC, but this is in the lower case. And similarly the impedance of the neutral line is denoted by Zn, N is small letter. So the schematic of this star-star connection can be represented like this: star with neutral ground, and on the lower voltage side also it is star with neutral ground. So this is the schematic representation of this particular star with neutral grounded on both HV and LV side. Now suppose if the neutral is not grounded, suppose we don't have this neutral, there is no written path for these currents to flow. That means this particular network acts as open circuit for zero sequence current. Okay, see, if you just assume that there is no neutral wire, that means all the currents are entering here, but there is no written path for these currents to flow. So in that case it acts as open circuit. But when there is a neutral path, that means that all the sum of these currents flow through this neutral line. So there will be a path for the currents to flow, and in that case we can consider this as short circuit. But when there is no neutral grounded, then we have to consider this as open circuit. So that was what written here. If neutral is not grounded, then there is no written path, and this acts as open circuit for the zero sequence current. Now if neutral is grounded, there is a written path, as I have said, and the total impedance that flows will be given by 3 times Zn. This depending upon the current equation, we are going to get this 3. It is not, but the Zn is the actual impedance of the neutral wire, but this 3 comes depending upon the current equation which we write. Okay. Now suppose instead of star I have delta connection on the LV side. So the phases are represented like this: A, B and C, and these are the low voltage windings, and these are the currents which are flowing in this. Now if you observe, these currents will flow within these windings only. They will not come out of these windings and flow through the lines. So that's why the zero sequence currents flow within the windings, but they cannot flow in the lines. So you have to keep in mind that when there is a delta, no current flows through the lines, but the current flows within the windings. And when we consider star connection, if there is no neutral path, we have to consider it as open circuit, and if there is a neutral path, or if it is the neutral is grounded, then we have to take it as a short circuit. So here we will be discussing different cases. The first one is star transformer with neutral grounded, that is on both HV side and LV side the neutral is grounded. The actual reactance of the winding is JXL. Now if you consider on the HV side, it is star with neutral grounded. So I am saying it as neutral grounded. That means there is a path for the current to flow through the neutral. So that's why I am considering here. I have just represented in terms of switch here to represent whether it is short circuit or open circuit. That is whether it is neutral, there is a neutral path or not, that is going to be represented by this switch. So since there is a neutral path, so I have to short circuit this. And what is the impedance due to this? That is nothing but 3 times Zn, the high voltage side impedance, since that's why I am representing it by capital N. Now when you take the low voltage side, even this is neutral grounded. That means there is a path for the currents to go. So that's why even on the low voltage side it is short circuit. So both sides current will flow since neutral is ground. This is the zero sequence network for star transformer when both the neutrals are grounded. Now coming to the next case, star with neutral grounded to star transformer. That means the lower voltage side the transformer is not grounded, not neutral grounded. So if you observe, since this is neutral grounded, there is a path for the current to flow. That's why on the high voltage side it is short circuited. But on the low voltage side there is no neutral grounded. That means there is no path for the current to flow. That means it acts as open circuit. That's why the switch is in open position. That is represented by open circuit. And since this is short circuited, the impedance of the neutral line comes into picture, which is denoted by 3 times Zn. So here no path for zero sequence current to flow since no written path. That is why here I am considering it as open circuit. So the next case is star transformer. So on both sides the neutral is not grounded. That means there is no path for the currents to flow. Now since there is no path, we know that it is open circuit. So on both sides, on high voltage side and low voltage side, it is considered as open circuit. The switch is open. The reactance will be J times XL only. And coming to the next case, star with neutral grounded and delta transformer. Star neutral grounded means, as we discussed earlier, this is short circuit, that is there is a path for the current to flow. And coming to the delta connection, see, I have said that the currents will be flowing within the windings but not in the lines. This is the line, and if you consider this, this is the winding. So there is one more switch placed here when there is a delta connection. So the current will not flow in the line but it flows through the winding. So that's why this is short circuited and here it is open circuited. And since here it is short circuit, the impedance of the neutral is considered, it is 3 times Zn. So as it is mentioned here, in delta connection, zero sequence currents does not flow through the lines and flows only through the winding, which is represented as above. Now coming to star delta transformer. Star delta transformer, star, there is no neutral path, so it acts as open circuit on the high voltage side. And coming to the delta, that means there is no current flowing through the line but it flows within the winding, so this becomes the short circuit, right. And the next case is delta delta connected transformer, where these two will be open circuit and the currents will flow only through the windings on both the high voltage side and the low voltage side. That's why these two are short circuited. So this is all about the sequence networks of three-phase transformer. See, the positive sequence and negative sequence networks are not going to be affected, but whereas the zero sequence network is being affected, whether it is delta or star connected or neutral grounded and all. So depending upon those connections, we are going to obtain this networks. So this is about the three-phase transformer sequence network.